So far, the basic construction and function of the power steering system has been explained. In a real automobile, however, various other mechanisms are added to improve steering feel. Steering effort varies with vehicle speed, and the required steering effort is less at higher speeds. From the driver's standpoint, the ideal would be for the steering assist to change in accordance with the vehicle's speed. For example, when the driver has to turn the vehicle sharply at a low speed, as when parking a car, the vehicle should be able to be steered with little steering effort. On the other hand, during high-speed driving, the steering wheel should be firm, yet responsive. In order to attain this goal, various systems are utilized so that the assistance will be provided in response to vehicle speed. Let's take a look at two typical systems: engine speed sensing power steering and vehicle speed sensing power steering. This graph was used during the explanation of the Vane pump. It shows the relation between engine RPM and the flow volume of the power steering fluid. In engine speed sensing power steering, when the engine RPM increases, the flow volume of the fluid generated by the Vane pump decreases, as shown in the graph. For this reason, the required steering effort is increased by reducing the assistance. Now let's take a look at the mechanism that reduces the flow volume. In engine speed sensing power steering, a control spool is added to the flow control valve of the Vane pump. This is the control spool. Located between the control valve and the orifice, the control spool reduces the flow volume of the power steering fluid by closing off part of the orifice. When engine RPM is low, the hydraulic pressure from chamber A is applied to the control spool. Although this should be enough to move the control spool to the right, the spool cannot move because pressure is too great, so the flow volume of the fluid does not decrease. This corresponds to the point shown here on this graph, which we saw earlier. As the engine speed increases, the hydraulic pressure in chamber A increases, so the control spool overcomes the tension of the spring and begins to move to the right. The pressure in chambers B and C decreases because the orifice is gradually closed. This creates a large difference in pressure between chamber A and chamber C. The flow control valve moves to the left due to this difference, and a lot of fluid is discharged, causing the flow volume of the fluid to the power cylinder to decrease. As the engine speed further increases, the control spool closes off more of the orifice. But even if the engine speed is further increased and the hydraulic pressure in chamber A also goes up, the flow volume of the fluid to the power cylinder is kept constant because a lot of fluid is discharged to the suction side of the Vane pump. This corresponds to this point on the graph. This is how engine speed sensing power steering reduces the assistance given when engine RPM is high. This produces an agreeable steering feel by providing appropriate steering wheel response even during high-speed driving. In vehicle speed sensing power steering, based on signals received from the vehicle speed sensor, the ECU controls the current to the solenoid valve in the steering gearbox in accordance with the vehicle's speed, thus controlling the steering effort. Now let's discuss one type of vehicle speed sensing power steering, the hydraulic reaction progressive type. The features of the hydraulic reaction progressive power steering system are as follows. A hydraulic reaction chamber is provided inside the control valve housing, and as the vehicle speed increases, hydraulic pressure makes the torsion bar more difficult to twist, with the result that the steering wheel becomes heavier. In this way, a torsion bar that is thinner than in an ordinary power steering system is used to reduce steering effort during low-speed driving. In the construction of a hydraulic reaction progressive power steering system, a solenoid valve, a flow dividing valve, and an orifice have been added to the previous power steering mechanism. As current from the ECU increases at low vehicle speeds, the opening of the solenoid valve also increases, decreasing the pressure in the hydraulic reaction chamber. The flow dividing valve channels the fluid from the vane pump to the hydraulic reaction chamber. This is the construction of the hydraulic reaction chamber inside the control valve housing. When the pressure in the chamber increases at higher speeds, the plunger uses that pressure to push the control valve shaft in the opposite direction from that in which the steering wheel was turned. This increases the steering effort. Now, let's see how hydraulic reaction progressive power steering operates. A passage leads to the hydraulic reaction chamber through the flow dividing valve, and a special circuit controls the flow of the fluid by means of the solenoid valve, which is located midway in the passage leading from the pump to the power cylinder. Since the solenoid valve is wide open at low vehicle speeds, the fluid that goes through the flow dividing valve returns directly to the reservoir via the solenoid valve without passing through the hydraulic reaction chamber. This allows the steering wheel to be turned with little effort because the hydraulic pressure does not react against it. In the medium to high speed range, the solenoid valve is gradually closed as the vehicle speed increases, so the pressure in the hydraulic reaction chamber rises because the fluid is flowing into the chamber. This makes for a heavier steering wheel. What will happen if the steering wheel is turned sharply in the medium to high speed range? In this case, the hydraulic pressure in the power cylinder will rise. The resulting high pressure will be transmitted to the hydraulic reaction chamber via the flow dividing valve and the orifice. This will cause the steering reaction, that is, the feedback to the driver, to increase in accordance with the operation of the steering wheel. When the steering wheel is turned further and the hydraulic pressure in the power cylinder reaches a predetermined value, the flow dividing valve moves downward and closes the passage to the hydraulic reaction chamber. When this occurs, access to the chamber is limited only to the orifice. Because the increase in pressure in the chamber is restrained in this way, steering effort does not increase to any great degree. This is how hydraulic reaction progressive power steering produces an agreeable steering feel by utilizing precise feedback control proportionate to the vehicle speed from the low to high speed ranges. In the on-vehicle inspection of the power steering system, we will concentrate on the hydraulic system because it greatly affects the steering assist provided. Now let's take a look at the points to be checked. First, check the tension of the drive belt, which drives the vane pump. Next, check the power steering fluid. With the engine idling, turn the steering wheel from lock to lock several times to boost the temperature of the fluid to about 80 degrees Celsius or 176 degrees Fahrenheit. This must be done because the level of the fluid changes depending on the temperature. Now stop the engine and check the level of the fluid. If there are any air bubbles in the fluid level will drop when the engine is running because the air will be compressed. So be sure to check the level again while running the engine and confirm that there is no difference. In the event that the power steering fluid is low, ATF Dexron or Dexron 2 should be used. Next, check the hydraulic pressure. Use this pressure gauge. First, disconnect the pressure line from the steering gear box. Then connect the inside of the pressure gauge to the pressure line and the outside to the steering gear box. Now, run the engine at idle. Close the pressure gauge valve and check the hydraulic pressure generated by the vane pump. During this check, make sure the valve is not kept closed for more than 10 seconds because high pressure will be applied to the hydraulic circuitry and could damage it. If the hydraulic pressure is lower than the standard value, the vane pump is probably faulty. Next, open the pressure gauge valve all the way. Then run the engine at 1000 RPM and check the hydraulic pressure again. Do the same at 3000 RPM. The difference in pressure should be no greater than the specified value. If the difference in the hydraulic pressure is greater than specified, the flow control valve is probably faulty. Next, with the pressure gauge valve still open all the way, turn the steering wheel all the way to the right and check the hydraulic pressure. Then check the pressure again after turning it all the way to the left. If the pressure is lower than the standard value, it means that the control valve cannot control the hydraulic pressure properly, or that the steering gear box has an internal leak. By checking the hydraulic pressure in this way, you can determine whether there is a fault in the vane pump or in the steering gear box. Next, use a torque wrench to determine whether the required steering effort is appropriate. Turn the torque wrench a quarter of a turn counterclockwise and check the torque. Then a quarter of a turn clockwise and check the torque. When you do this, the results will differ depending on the coefficient of friction between the road surface and the tires. So steering effort should be checked on a flat paved surface using correct size tires inflated to the proper pressure. For more detailed check methods, including the standard value for the hydraulic pressure, refer to the repair manual for the appropriate vehicle model. We are sure you can now understand the mechanism of the power steering system, which produces the proper steering feel. We hope that the knowledge you have gained through this video will help you to serve your customers more effectively and efficiently.